So, next problem is for an endothermic reaction in forward direction, if the temperature of the reaction mixture is raised, what will happen to its backward reaction? So, rate of backward reaction will decrease, right? Rate of backward reaction will decrease, okay, because increase in temperature equilibrium shifts, equilibrium will shift in the direction in the direction of so this is endothermic reaction. Okay, and decrease in temperature equilibrium shift in the backward direction, right? Exothermic reaction. So, for exothermic reaction, if we decrease the temperature, it will move in the backward direction, but for since this is the reaction in the problem, it says that the endothermic reaction in the forward direction. So, if we increase temperature, okay, so equilibrium shift towards the products or this side, right hand side. So, the rate of the backward reaction will decrease. Next, we move to problem number 12. It says, in which of the reactions the equilibrium will remain unaffected on addition of catalyst. Okay, so addition of catalyst does not affect the equilibrium, right? So for the both for the first and second reaction, it will be it will remain unaffected. So option 3 is the correct option. So option 3 is the correct option. Option 3 is correct. Okay, as catalyst does not affect the equilibrium. Move to problem number 13. For the reaction COCl 2 minus plus 6H2O gives COH2O 6 plus 4Cl minus. Overall, the color of the solution is blue. If it is diluted, what will the final color at equilibrium? So dilution means we are adding more color to it. Okay, so if we add if diluted more water added, right? So concentration of H2O increases, right, with dilution. Okay, so concentration of H2O is there in the reactant side, and in the equilibrium constant it is in the denominator, right? So as per Le-Chatelier principle, okay, when concentration of reactant increases, the equilibrium shifts to the forward direction. The equilibrium shifts towards forward direction. So, with dilution, the final color will be pink, right? Because this complex is pink in color, okay, the final color will be pink. This was very interesting problem. Next we move to problem number 14, which says for the reaction X is in equilibrium with Y, the equilibrium constant is 1.1, which gas has a molar concentration greater than 1. This is again very simple problem. Okay. So, the reaction is X gas is in equilibrium with Y gas, right. So, given Kc is concentration of Y by concentration of X, is 1.1, right. So, concentration of Y is concentration of X times 1.1, right. Now, there will be three cases, right. Case 1 is if concentration of X is 1, then concentration of Y is 1.1. So, greater than 1. Case 2, if concentration of X is less than 1, then concentration of Y can be greater than 1 or concentration of Y can be less than 1, depending on the value of concentration of X, right. Okay, so, this is another case, case 2, and case 3 is this one. Okay, so so case 3 is this one. Okay, so case 2 and case 3 we can club actually. So, if concentration of X is less than 1, then concentration of Y can also be less than 1. So, this is greater than 1 and this is less than 1. This is also a very simple problem. We move to problem number 15. It says the synthesis of glutamine from glutamate ion and NH4 plus ion is unfavorable as per the standard Gibbs free energy value. So, glutamate reacts with NH4 plus gives glutamine and delta G naught value is given. How could the hydrolysis of ATP be used to render usable for the synthesis of glutamine? Okay. So, the original reaction is glutamate is negatively charged plus NH4 plus gives glutamine with delta G naught value is given 14.3 kilojoule per mole, right. The original reaction, this is the original reaction, is affected by using ATP. The new reaction which is thermodynamically favorable consist of two partial reactions. Like partial reactions. Okay, so through a common intermediate via ATP hydrolysis. So, glutamate minus plus ATP 4 minus gives 5 phosphoglutamate plus ADP, ATP converts into ADP, ADP 3 minus, and 5 phosphoglutamate reacts with NH4 plus, gives glutamate plus phosphate minus. So, delta G naught for this reaction is minus 30.5 plus 14.3 kilojoule per mole. So, gives you minus 16.2 kilojoule per mole. Since the value is negative here, so this is thermodynamically favorable. Hence, it is. So, for the first reaction the value of delta G naught is minus 30.5, and for the second reaction it is 14.3. So, basically it gives you for this thermodynamically favorable. The enzyme glutamine catalyzes this reaction, catalyzes this reaction in the animal cell. This is a little bit complicated problem. You need more information to solve this one. So, we move to problem number 16. It says creatinine phosphate plus H2O gives creatinine plus PAI. Delta G naught value is given minus 43.5 kilojoule per moles, and ADP plus PI gives ATP plus H2O. Delta G naught value again given 39.8, here is positive kilojoule per mole. Calculate standard free energy and then the equilibrium constant for this reaction. So, if we add these two reactions here, okay, then we get this third reaction. So, we need to add delta G naught. Okay. So, for the reaction creatinine phosphate creatine phosphate plus ADP is in equilibrium with creatine plus ATP delta G naught is minus 43.5 plus 39.8 kilojoule per mole. So, if we do it, we get the value is minus 3.7 kilojoule per mole. So, once we get the value of delta G naught, we can calculate equilibrium constant. Okay. So, for the equilibrium constant, we consider temperature T. So, we consider 300 Kelvin or 298 Kelvin. Okay. So, considering, so we know delta G naught is minus RT ln K, where K is equilibrium constant. So, considering T is 2 or 98 K, we can write minus 3.7 times 10 to the 3 in joule unit is minus R again in moles in joule unit. R is 8.314, temperature is 298 we are considering, and then we get ln K. So, we get the value of ln K is 3.7 times 10 to the 3 by 8.314 times 298. So, the value of K we get is 4.6, something like that. So, this was problem number 16. Next we move to problem number 17. For the reaction H2 plus I2 gives 2 Hi, the equilibrium constant is 16 at 500 Kelvin. If 2 moles of hydrogen and 3 moles of iodine are injected, then what will be the concentration of all the species? Okay. Suppose, let us consider that n moles per liter of hydrogen react, this will react with n moles of iodine, you see 1 and 1 here. Okay, so, n moles of iodine. Right, and forms 2n moles of Hi. So, we consider, let us consider n moles of hydrogen. Okay, fine. Okay, so then the concentration at equilibrium are concentration of H2 is 2 minus n, concentration of I2 is 3 minus n, and concentration of Hi is 2n. Okay, fine. Then K is, because we started with 2 moles of hydrogen, so n moles react. So, now at equilibrium concentration of H2 is 2 minus n, and 3 moles of iodine. So, initially we started with 3 moles of iodine. So, n moles of iodine react. So, we get concentration of iodine is 3 minus n, and when n and n moles of hydrogen and iodine react, so we get 2n moles of Hi. That is what we got here. So, now you can calculate equilibrium constant. Now, equilibrium constant K is concentration of Hi raised to the 2 by concentration of H2 times concentration of I2. Okay, so what is the value of equilibrium constant? Is 16 is 2n to the 2 by 2 minus n times 3 minus n. Okay. So, what we got is 4 times 2 minus n times 3 minus n gives you n square. Okay. So, we get here, if we solve it, we get 3n square minus 20n and plus 24 gives you 0. Okay. So, if we solve it, we get the value of n. Okay. So, we get the value of n is n you can get 1.56 or 5.1. This we got. So, n is plus minus 20 plus minus b. So, minus b is 20, minus 20 gives you plus 20, plus minus root over b square means 400 minus 4ac. 4 times a is your 3 times c is 24 by 2a, 2 times 3. So, if we do it, we get this. Now, this cannot be possible, right, because we started with 2 moles of hydrogen and 3 moles of iodine. So, 5.1 moles of hydrogen cannot react. So, this is not possible, right. So, we need to consider only this one. Hence, concentration of H2 is 2 minus 1.56, because we started with 2 moles, now 1.56 moles of hydrogen reacted. So, we get 0.44 moles. Okay, and then concentration of I2 is 3 minus 1.56. So, we get 1.44 moles, and concentration of HI 2 into 1.56, so 2n, so we get 3.12 moles. Okay. We move to problem number 18. It says for the reaction 2NO plus Br2 gives 2NOBr in a closed container, 0.087 moles of NO and 0.437 moles of Br2 is mixed at constant temperature to form 0.518 moles of NOBr. Calculate the amount of NO and Br2 at equilibrium and their corresponding equilibrium constants. Okay. So, concentration of NO at equilibrium is 0.087 minus 0.518. Okay, 0.518. So, you get 0.0352 moles. Okay, similarly, (0.0518) moles of NOBr will be formed, because 2 moles of NO gives you 2 moles of NOBr. So, 0.0352 moles of NO gives you 0.58 moles of NOBr. Okay, from 0.0518 by 2 moles of Br2. Okay, so you get concentration of Br2 at equilibrium is 0.0437. We started with, I reacted is 0.0518 by 2. Okay, so if we do it, we get 0.0178 moles. So, equilibrium constant K is concentration of NOBr raised to the 2 by concentration of NO by raised to the 2 by concentration of Br. Now, we substitute the values of NO, Br, NO and Br2. So, if we substitute this, we get for NO, Br is 0.0518 raised to the 2 by 0.0352 raised to the 2 times 0.0178. So, if we carry out further, we get 121.66. Next, we move to problem number 19. It says A2 plus B2 reacts and gives to X2, and delta H for this reaction is given x kilojoule. Which temperature and pressure condition will favor the maximum product? So, here delta HR is negative. Okay, so this is exothermic reaction, low temperature and high pressure. So, this is exothermic reaction. Right. So, decreasing temperature C will shift to forward direction. Decrease in temperature, and we increase the pressure also, decrease in temperature and increase in pressure. Because you see less number of products are formed in the forward direction. Okay, so if we increase the pressure as well as decrease the temperature, we will shift to the forward direction. Low temperature and low pressure. So, we are decreasing temperature and pressure is also low. Okay. So, low temperature, okay, so which temperature will favor the maximum product? So, the one will be the correct, okay, second and third, fourth will not work. Okay, next we move to last problem. As per last Atelier principle, adding heat to solid gives liquid equilibrium will cause temperature to increase, temperature to decrease, amount of liquid to decrease and amount of solid to decrease. Okay, so, melting process is endothermic process, right? We need to give heat. So, melting process is endothermic. Okay, heat needed, right? Heat needs to be heat added. Okay, so if we add heat, the system shifts to consume the heat, means shifts towards the liquid state. But the temperatures remain constant, right? During phase transition, temperature remains constant. Temperature remains constant during phase transition. Because solid to liquid is phase transition, and it is in equilibrium also during phase transition. So, when heat is added, solid decrease and liquid increase, right? But no temperature change. But no temperature change. So, 4 is the correct option.